Okay, you will online. Can you hear me? Yes. All right. Good job. So, let's start with the exam. So I started grading the exam myself, so that I need to know, I see myself what you guys did, and so it's taking me really longer than what I thought. So let me just show you the solution so that at least you would know what you did, and then hopefully within a few days you will get the solution. So problem number one. Problem number one, he just wanted to plot a cycle, a reheat cycle, and an ideal reheat Rankine cycle with high pressure turbine and low pressure turbine. So he expanded the turbine, take it to the boiler, reheat a little bit, and come back to the low pressure turbine, and then all the way to the condenser, pump, boiler, and so on and so forth, right? And he gave us the pressure, the boiler pressure. Okay, is this much? Is that the boiler pressure? Is it the same as high pressure turbine pressure? It is. The boiler, the pressure of the boiler where it heat at, the boiler actually we assume, by the way, we assume that the boiler is at constant pressure, right? But is it really true? When we plot any boiler on a TS diagram, what do we usually do? We do. Make it a little bit bigger. So on the boiler, on a TS diagram, we usually go like this, then this, and then this. What is that line that I'm plotting here? Constant pressure. And we would say like the water go into the boiler at say state whatever 4 or 15, and then it leave at state 1 ready to go to the high pressure turbine. And if there was a reheat, you would take it here at that pressure, you reheat, and then you will heat up till here, or sometimes they heat all the way up to the original temperature. Okay, and then they expand again. So this constant pressure, is it true or not? Is that a good assumption, or actually is this what happened in real life? Or do you think it's not true? It's not true because the Jenks power plant that we saw in the homework, when you look at the pressure going into the boiler and the pressure coming back from the boiler, they are different. And that means there's a pressure drop between the inlet and the exit. And that makes sense because this boiler is 14th floor high with a lot of pipes. How do you expect water to go into 14th floor worth of pipes and come back to you frictionless? How is that going to happen? It's not going to happen. So in real life, it's probably coming at a little bit lower pressure, right? But in all undergraduate, Rankine cycle, we always assume, what is, 100 psi between friends, and the whole thing is running at say 2,000 or 3,000 psi. So if you drop 100 over 3,000 total, it's not really a big deal, right? So again, in homework 6, let's check homework 6 for. That's homework 6. When you look at this, what is the pressure coming into this boiler? You see that 4,000? You see it? 4,200, right? Where? 4,227. That's the pressure coming in. And the pressure coming back is how much? 3,500, right? 3,500. So 4,235. 700 out of 4, or it's like what, 1/6, right? 700 over 42,000. So 1/6 pressure drop. So that's totally understood. That there is pressure drop, and and you just have to, in real life it will happen, right? So he wants us to do this pressure. This is the boiler pressure, and it also happened to be the turbine pressure. Ideally speaking, those are the same thing, right? And here's the inlet temperature of the high pressure turbine, 1000 Fahrenheit, which also the exit of the boiler. I mean, the boiler give you the pressure and the temperature that go into the turbine. So this is point 1 in my TS diagram. That's when I leave the turbine, I go into the, I leave the boiler and go in the turbine. Right? And the inlet temperature of the low pressure turbine is this much, 1000. So he managed to take it all the way up to the same temperature as the high pressure turbine inlet. And its inlet pressure is this. What is that inlet pressure of the low pressure turbine? That is the heat pressure. Again, ideally speaking, it is, but in real life, I mean, you can just check here and you would see that the pressure going into the reheat is how much? You see 695. Right? Isn't that the pressure going to the reheat? And coming back from the reheat, 625. Right? So again, bunch of pipes, bunch of valves. I mean, don't expect it to go frictionless without anything. It will drop a little bit. But we always plot it basically at constant pressure. All right? So how do we plot this cycle? The cycle that was given to us is SI. The temperature is in degrees C, and those pressure line. You see those pressure line? What color is the pressure line? Is it the orange or the dark brown? Dark brown, right? The dark brown is the pressure line. I was shocked. I didn't grade problem number 1 was first. I graded actually problem number 2, but I thought it was easier because just like one equation. So I said, let me finish it and get rid of it. But like I will always catch problem number 1 in the way to problem number 2. And I saw horror figures. It is like people some still don't know what is a constant pressure line. They plot like really weird things. So let's make sure we understand what is a constant pressure. It goes like this until you hit, this is saturation valve, saturation vapor line. And then once you are saturated vapor, when you go, you get superheated along this line. That is the constant pressure. Keep heating, you go up, 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 up. Right? And we said before the exam, how I told you for the exam, how all those pressure line, they are all coming along this small band. They are so close to what is that edge of the dome. That line is the saturated liquid line, right? So from saturated liquid to the highest pressure ever, you still have to fit here. You are here, right? So I saw some people coming at, the condenser exit like this and then going up like this. That's the boiler, the pump, and then going like this. That's okay for a cartoon when you're trying to say here is the pump, but when we are actually plotting it on this actual TS diagram, the pump will show up as what? As a dot. The pump will show up as a dot at 50 degrees C, because I mean, where it will go to nothing, right? And I want you to see this and remember it. When you take 4263 and you see them neglecting work pump, you will understand. You will sympathize with the author, like why he's neglecting work pump, because you remember that this thing was like a dot on the TS diagram compared to the boiler, the turbine that go all the way up from here to here. Huge work in the turbine. Very tiny work for the pump. And that big difference, by the way, is the beauty of the Rankine cycle. Is that we get all this from the turbine and we take this much to go to the boiler pressure in the other side. right? So that's what's actually cool about it. So here is actually the one of the best solution. Again, I was not really grading, but just like flipping, and I only flipped. I went through half the class, so maybe someone else from the bottom of the class, from like 15 to like 30 to 55, had even better figure. But up till what I saw that was the best figure. Okay, so that student basically, in his solution, he said, well, I need to convert this 1000 Fahrenheit. What is that? And so he converted it, turned out to be 537. So he put a line at 540, more or less, a little bit smaller than 540. And he said, those are my high pressure and low pressure turbine. That's how high I will heat. And then he converted the pressure, he or she, I don't know who's that student. So when I grade, I actually don't look at the name. And if I ever see who's the name, I try to completely don't see the paper and start from somewhere else so that I wouldn't be biased when I'm grading. So I don't know who did this, but anyway, so that student, he converted the pressure to 41 bar and 43 bar. So he came to 401 bar, right? And he put it like this. And so he realized, or she realized, that it's above the critical point. The critical point is how much? 220 something, right? So, I mean, I'm gonna look for that. I mean, you have to, this point, it has to be above the dome. One student plot the cycle like up till here, like he came here, and then he went constant pressure like this, and then reheat. I don't know what is that, why? So those lines are the pressure line. You understand what I'm saying, what he did? That student on the TS diagram, he went like this. So what is that? Right? So we have to follow the constant pressure line. All those are constant pressure line. And when you are subcritical, you move like this, and then you go up like this. Make sense? But above the critical point, the pressure line become like this. Right? So there is no such thing as something like this. That does not exist. There is no such thing. Yeah, you have to either go up like this. You have to go up like this, and then expand, and then you go to the heat pressure, expand. So you go here, expand, and then, right? And by the way, not related to this problem, because this problem you were giving that pressure, but what do you think, what is the optimum pre-reheat? Because in the next project, we're gonna decide this. So what do you think the appropriate pre-reheat is? Anyone? It should be 75% of the B boiler. So when the pressure is 75% of the boiler pressure, more or less, it's not etched in stone, because I mean, depending on what other equipment you have. But if you are 75%, that can give you maximum improvement in the efficiency. Okay. All right, so that this is the solution. You just go to that temperature at that pressure, and then you will go expand isotropically, because he said it's ideal, not real. If it was real, it would have gone like this. 4S would be here, and 4 would be like this, right? And you expand, sorry, you reheat on that pressure, right? The 43 bar, until you hit this temperature, and then you expand again isotropically. all the way to what? To 50 degree, right? 50 degree here, right? And you see how that student made 1 and 2 on top of each other because he realized that there is no room. I have to make my pre-boiler and after, sorry, pre-pump and after pump test condition almost the same. Good? Yes.
I've got a question about the technique of 75%. We have solved it using Xgame to find the S value, which would go up and coming out, you know, assuming.
So which point you are talking about?
So point 2.
Point 2, like you're saying, how can we find point 2?
Well, I'm saying what I did, and I'm wondering if it's.
Okay, tell me what you did for point 2, because point 2, what do we know about point 2?
So we knew 625 psi.
We know the pressure, right? We know it's 43 and 34, 43, and we know that it is under 1.
Right. So
why it's under 1?
So that's kind of what I did. I came down to a specific point and then back up. I was thinking to do it that way rather than saying the 75% of.
No. The 75% is not related to this problem. I said unrelated to the exam. That ideal pressure is 75%. In this exam, no, we were given that pressure, right? He said we want to go down to 625 psi.
Okay.
I'm just saying that if someone asking you to design a heat cycle and you're like, how much should I go before I reheat? I'm telling you the golden rule is to go to 75%. But in this problem, we were given exactly 0.2 or like whatever this point is. We were given its pressure and we know that it's isentropically expanded. So all the way down until you hit that pressure, right? Sorry about the confusion. All right. So the number 2. So number 2, he's saying that we have this big pump. This big pump, they call it the boiler feed water pump. Boiler feed water pump, because that is the pump. Yes, there are like 2 other guys, but those are tiny. Condensate pump, when you look at the pressure difference they make, it's nothing, even this one. But this is the guy. And I remember I said in the class that this guy is so big, this pump is so big that extent that they don't run it with electric motor. I remember I said in the class they run it with a steam turbine, because why would they turn the power into steam into electricity and then use electricity to run the turbine, sorry, to run the pump and lose losses in anywhere? I mean, if all it needs is mechanical work, we have turbines, we have steam. Let's make the mechanical work of this for this pump ourselves by that turbine. So I see the boiler feed pump turbine, and I pointed it with green and green so that you guys can see them. Okay, and so here, every time I zoom in, I don't know why the Microsoft just like jumping up. Any reason why? Like I expand and the page completely flip. Why is that? So anyway, so he's coming here, inlet and exit. Turbine, right? It get bigger. It's clear. This is the inlet with the arrow also direction, and this is the exit. So what is this number? 1321.5 H. Enthalpy in. And what is this 1054.5 H? Enthalpy out, right? And before the exam, I said, when someone asks you about the boiler heat transfer, what do you say? M dot delta H. When someone asks you about the work of the turbine, how much it is? M dot delta H. When I'm asking you about the pump work, how much is it? M dot delta H. I said everything is M dot delta H. Just write M dot delta H and you'll be fine. So in this problem, this turbine is running this pump. Okay, this pump is moving 3 million pounds. Huh? of steam from this to this condition. From this H 404 to this H 420. What's the difference? 420 minus 404. It's actually 420.7, 404.6. How much is the difference? 16.1. He even did the subtraction for you. And he said this takes 16.1. So this pump take the steam from H 404.6 to 420.7. How much steam does it, or water does it pump? 3 million.2. So if someone asks you, what is the pump work? You would say m dot delta H. The 3 million multiplied by the delta H. This H minus this H. Is that hard to get? We need to remember that. Pump work m dot, it's delta H, the H before and after. I saw people doing the pump work is m dot, the 3 million multiplied by this H minus this H. Why? Why this pressure, why this insult is even in the story? I didn't get it. So it's m dot delta H of that pump, right? That is the pump work. Now, who's paying for that work? Who's supplying that work? The turbine with its own m dot delta H. And he's asking about this m dot. So how do we get that? We would say, what's the solution, guys? Work turbine, work of the boiler, feed pump, turbine. Work turbine equal work pump, right? So you would say this. What's the work turbine? M, mass of that boiler, feed pump turbine, delta H, its own delta H, I mean turbine. Let's subscript this. Boiler feed pump turbine. Equal to M water multiplied by the delta H of the pump, right? Of the boiler feed pump. Right? And this, let's make, I mean, this is M water, but also happen to be the flow rate going through this pump. So I have the delta H across the turbine, and I have the flow rate and the delta H across the pump. Okay, and so you make this equal to this, and then you get the flow rate. So out of like 30 people I graded so far, like maybe 3 people got those numbers right. Everyone else had like weird numbers because they used those H's, and they, for example, they said the work turbine is work net minus Q condenser, like really weird things. Okay, so this part, you know, I was hoping that some of you will even, you know, say let's make this number even real. And I didn't finish grading, so maybe some of you already did this. You would say that you don't expect a turbine sitting next to a pump and send the work, you know, 100% proof between them. What do you expect in between? Is there any losses between a turbine and a pump sitting at the same shaft? There is bearing, right? Bearing losses, mechanical losses. Maybe they don't run at the same speed. Maybe there is a gearbox between them. So kind of eta mechanical. And I mean, if you just assume one, but you write some kind of eta mechanical, that show like really great understanding of what is the physical system actually look like, right? But so far, I didn't see this happening. And anyone who just like at least 2 out of 30 managed to write this equal to this and get the number right. Right? So was this hard? Was this problem hard? Work pump equal m dot delta H, work turbine m dot delta H. Why this problem was not really done correctly? Anyone wanna offer an explanation? It was running out of time, but m dot delta H, you know? Right. Okay. But did you get the right delta H? Why not? What, like this part was easy, I guess. Most people got this. It's like maybe this part was not easy. Maybe the 105 is not clear to the eye. People don't see it as well.
I just didn't have enough time to dissect it and look at it. That's why it's a little more than an hour to do the problem.
Okay.
I got fun.
All right. Number 3. So number 3, mechanical vapor compression cycle. And give us, to save our time, he give us all the H's. All right. We know how mechanical vapor compression look like. Gonna be H diagram. It look like this, 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 this. Here is one. Sometimes one is like superheated. Here is 2, and this ideally would be constant S. And not ideally, it could be, you know, a little bit off to the right. Doesn't matter. We got 2, and here is 3. And again, ideally, it could be saturated, but in your life could be a little bit subcooled. And here is 4. This part is Q dot L. This part is work dot compressor. This part is Q dot H, right? Piece of cake. What work compressor? M dot delta H. His delta H. What Q dot L? M dot delta H. Again, its own delta H. H1 minus H4. And this Q dot H is M dot delta H. I guess you will leave this course remembering that it's M dot delta H, right? Stuff are M dot delta H. So he gave us this work compressor. I mean, of course, he gave us also all the H's. So that's a relief, and that takes a lot of time to actually get them from table. So he gave us this, and he's asking for this. So what do? We use the first equation to get what? To get M dot and put it in here. So I didn't grade this part yet, and hopefully this is easy enough, and a lot of you did a great job in it. So I'm crossing my finger. That is the case. That problem will save the day. Right? So here is the first part. Of course, what's not nice about this problem is conversion, but that's okay. I mean, you can always come and you Google what is horsepower to, you know, BTU per minute, or what's horsepower to ton, and you will get the conversion. But this horsepower is M dot delta H, and from that you get M dot delta H. So you get M dot. Okay. And then you come to the second equation. Q is M dot delta H, and now you got your M dot. You get your Q low, and then you convert it. Again, you Google what is the conversion, and they will tell you it's 8 ton. That's the third problem. Done? Good job. So our second exam is coming in what, in 3 weeks? I mean, let's look at the syllabus. So our second exam is November 1st. We're already here. So 1, 2, 3, right? And it will be mainly heat transfer and psychrometric, because we didn't do psychrometric in this exam. Right? This exam was all just like mechanical vapor compression and Rankine cycle, right? So I would say that the second exam is basically this psychrometric and heat transfer. Good. All right. So let's do there's something in the chat. So the chat, I think it was difficult determining which Insalbi value to use. Right, I agree. The Insalbi, especially that the chart is not really convenient. I mean, it's like so small, the font is so small. But, you know, my only excuse to give you this problem is that we went through this chart in many assignments. So you should have already went through the difficulty of understanding this chart before. Right? We had it in a bunch of things. And this is not fictitious chart. This is really how do they plot their cycles. So you need to be familiar with the notation and the way they actually put those cycles in on paper. Okay, so before we solve the homework, let's remember what we did last week. So what we did last week is that we said heat exchanger are basically a place where hot fluid gets cooled by a cold fluid, right? And so the cold fluid TC1 get hot and leave at TC2, while the hot fluid is being cooled to say TH2. And you can call this TCN and TC out and THN and TH out. And the fact remains that the Q that this guy get is the same as the Q that this guy rejects, right? So basically, there's only one Q between the two sides. Q dot is Q dot cold is Q dot hot, and we said this is usually M dot Cp multiplied by delta T. So if you're gonna do this at the cold side, it would be M dot cold Cb cold Tc out minus Tcn. Right? That's what we said. Good. So in the homework, he said, I want to do this for the condenser. Here is a condenser. He said this condenser is cooled by water, cooling water. Cooling water come and the cooling water leave 10 degrees hotter. And he's wondering how much is the M dot that is needed to do this. So how do we do that? He's asking about, I mean, we know that for any heat exchanger, and the condenser is a heat exchanger, the only difficulty between the condenser and this figure that or sketch that I plot is what? What's the difference? Anything different? Anything different between the condenser of a steam power plant and between this cartoon? Free quiz today, if you answer that. You don't have to solve the quiz today. The question is, this cartoon of a heat exchanger, how is it different from the condenser that we are dealing with in homework number 6? No, it is going to be like this. It's counterflow. It could be counterflow, really. I mean, it's not purely counterflow, but that's not the difference. I mean, I know you say counterflow, crossflow, because you see the steam falling from the turbine on the pipes, right? So it's not like they are doing like this. But some condenser, I mean, we don't see what's the design of the condenser. Some condenser could be counterflow. But there is another difference that I am 100% sure it will be there compared to that sketch without even opening that condenser. Huh? Anyone? Free quiz today.
Because we're adding in Q to make up water, to make up water,
Say that again.
Because we're adding in the make up water.
Make up water to the condenser? No, there is no make up water in the condenser. That's not a cooling tower. Huh? That's not a cooling tower. That's a condenser. We don't add make up water. In ideal situation, there is not. Of course, there is make up water. Don't get me wrong. Water leave and we have to add water, but it's not like for steady state operation. It's like, with some losses, let's add more. But in the cooling tower, that faucet is always on. The cooling tower faucet is always on because they are just like letting the water go all the way. So I was actually doing a consultation for a company, like having a big building in Tulsa, and they had like cooling tower for their chiller, and their faucet, the level of the water in the cooling tower, you know, they had those like float And when the float is up, that tells you the water is full, and you shut down the valve. But the float was wrong, it was like basically not really doing its job. And so they were like sending water. So I climbed up all the way, and it was like a rainy day just to see it. I told them I want to see up. And I went up, and the float was not working, and the water was just flooding the place. And so they were paying for the money to just keep adding water, even with no need, because the water level was okay. But they just like adding water and draining it. Anyway, again, what's the difference between this and a condenser? I'm gonna get my frequency. Condenser has more air.
Over the cold coils.
Condenser does not have air. The condenser has steam from the turbine and water from the river, the lake, the cooling tower, whatever we are bringing the cooling water from. So what is the difference between that sketch and the condenser? The cooling water does not change temperature? You were that close to get the frequency. No, it's the steam that does not change temperature, not the cooling water. The cooling water has to do this. The cooling water in need to go to the cooling water out, but the steam condense at constant temperature. Why does the steam condense at constant temperature? Because the steam is part of a Rankine cycle, right? Remember? The steam is doing this. The steam is part of this Rankine cycle where the pressure, the pump take him here, and you go up to the boiler, and then the superheat, and then the reheat, and then you go back. That is the steam, right? So the steam that's doing this, how is going from Hg to Hf so that he can become liquid, so that the pump can take him up? It's the cooling water, right? So that cartoon that we always make, for general heat exchanger, where one fluid, the car cooling fluid does this. He drop while the air cooling it go up, right? But the steam condenser have a constant temperature. Okay, so how is that going to make things different? Well, maybe here when you are trying to calculate m dot hot, you cannot say m dot Cp delta T, because delta T is, for the steam, delta T is 0. So what do? I still need my Q dot hot, man. So what do? M dot HFG, right? He turned from steam to turbine. Whatever this H, I mean, if he's saturated, then it's HF, it's HG. If he's a little bit wet, then, you know, it's like H whatever, 0.3 to H 2.4, say. So H3 minus H4. Okay? So we don't do m dot Cp delta T for the steam. You got that? Okay? And so this is actually what we said last time, right? This is what we said last time. So now H coming from the DLP. Okay, so here in this homework problem, he said, I want to figure out how much m dot water this guy is requiring, right? He said calculate, assume the where. Please calculate the required cooling water mass flow rate. So what I'm going to do, I'm going to say that Q in the condenser is m dot Cp delta T. The delta T, I guess it's delta T, right? This, we know how much, 10 degree, right? 10 degree Fahrenheit. This Cp, I know. How? Why? Because it's CB of water at room temperature. I can just Google what's the CB specific heat of water at room temperature, and it's like 418.4816 joule per kilogram Kelvin, more or less, right? It's a famous number because that's how they turn the joule to calorie, right? So we already got this. Actually, maybe we should label them. Okay. All right. So we know those guys, and what he's after, ouch, is the m dot. This is the unknown, right? This is the guy that we need to calculate. So obviously in this equation, then we need to find out what is Q in Q condenser, Q, which is Q rejected for the cycle. So how did you do it? How did you get the Q rejected in this cycle? In this big power plant, how did you figure out how much Q is rejected here in the cycle? How? So the approach is, you told yourself, I need to look at this big cycle, right? The big Rankine cycle that is basically, there is a boiler, and at the end of the day, there is work net, there is Q added, and there is Q rejected, right? So you mean boiler or work net? Yes, correct. The work net is 481 megawatt. That is correct. So if only we know, if we only can calculate Q added, if only we can know this, we can calculate Q rejected, because Q rejected from the first law would be how much? Q added minus work net, right? First law, Q added minus Q rejected, get work net. So, right? So we know work net, we are after Q rejected. So we need to find out how much is Q added to the boiler. How much Q is added to the boiler? Yeah, the m dot going in delta H plus m dot delta H. We did this in the homework before. We know exactly how much heat does the boiler takes. You subtract the work net out of it, and you'll find out Q rejected in the condenser, right? So Q added minus work net is equal to Q rejected, with, of course, the appropriate units, right? So someone was actually asking why are we given the m dot water that's going into the cycle? Because this Q added is m dot del H plus another m dot of the reheat, right? Time delta H. Right? This is Q added. Questions? Was this hard? Yes, no? Was okay, right?
I think the hardest part was reading the diagram, kind of understanding it all. I mean, it's the third, fourth time we've seen it, but I know I'm still struggling with it.
So why don't we discuss this diagram just in case I get excited about it one more time in the final? So what is in this diagram that's annoying you? I tell you myself, what's annoying me is all those symbols, like all those circles coming from, it seemed like nowhere. You're like, where is this things are coming from? Yeah, but you actually don't really need to, unless you are trying to fix the pipe, then you need to find, but you don't really have to deal with any of those, in order to solve any of the problem. You really need to focus on the big picture. What's the big picture? The boiler part, Any one of those feed water heater, what you need to understand is who's coming in and who's leaving. So as long as you are happy with this, you are fine. But you don't really need to know where those coming from. Doesn't make any difference. Huh? And see the makeup that you said about, that's the makeup when they add the new water. So that makeup, because of all the steam that could escape from the pairing. So you don't need to search for where T is coming from and where does it end. Huh? It ends here. But you don't have to worry about any of this. Anything else annoying? Say that again. DFL on the left. DFL on the left. DFLB, I just read this as the low pressure turbine. Now, why it's DF? I mean, diverge, I don't know, flow, diverge flow, or some, maybe it's like the flow is going this way. Dual flow? What is dual flow? Dual flow, yes, that makes sense. Yes. Yes, it is dual flow, correct. So basically that M dot is split between the two sides. And they let them sit back to back. Why? To balance the axial force. Because the thrust pairing, if it has axial force, you probably have studied this in MIG design too. Something, the axial pairing is like horrible. You want the bearing to have very small axial force. So that's why also the high pressure turbine and low pressure turbine are sitting back to back. It's not the same, but they are trying to balance it. So that the whole shaft is not under, severe axial force. I think it's intermediate pressure. So high pressure, intermediate pressure, and low pressure. And some diagrams, like I can give you a diagram with high pressure, low pressure, and two low pressure turbine. And each one of them is dual flow. Yes, high and low here, high and intermediate, and then this is the low. Right? I guess also what's confusing is like how the flow rate coming is split. Some go to M.7 and some go to the reheat. Right? But again, what you really care about is how much is going to the reheat. Right? But it's such a good, skill that you can look at those professional diagrams and you can understand them. So I would say it's worth every point that you lost so far on that. Right? It will pay off later on in your career. That you will hit the ground running. Yeah, here's diagram, sketch diagram. I know those things. I lost 30 points over them in my 3,524. Okay, so let's enough homeworks and exams and stuff, and let's move to designing heat exchanger. And we have a new project that is due in 2 weeks. So let's talk about this. So when I'm plotting the heat exchanger temperature, I usually plot against X, where X would be the distance of the heat exchanger. It's like, he's going like this in pipes, and the other guy go like this. The other fluid is doing this, while this fluid is doing this. And you are basically trying to say, well, along this x-axis, along this passage, what happened to my cold fluid? Okay.
It heats up.
I'm sorry, what?
So it would heat up.
It will heat up, yes. The cold fluid will heat up while the hot fluid will cool down, right? And so our problem is the right delta H for that. Sorry, the right delta T. Okay. What is the right delta T? I mean, if it's the same difference, if it's almost 10-degree difference between the hot and the cold, then that make our job easy. But sometimes it's not the same. And so we wrote two equations, right? We wrote Q is m dot C CBC delta DC equal to m dot hot CB hot delta T hot. But the second equation or the third equation that we need to write is the heat transfer equation, which say that this m dot, and what's the unit of m dot, by the way? Help. Units of m dot, sorry, of q dot is kilowatt, right? So the kilowatt is U A delta T. And that delta T, let me make it in green. That delta T that we are referring to is this. This is the delta T. It's the delta T between the hot and the cold, right? And so that is basically the problem of this delta T, right? So there is the method that we're going to deal with today is basically called logarithmic mean temperature difference. And it's a way to calculate the delta T between the hot and the cold. And so this equation is really the heat transfer equation, because those ones, that's really thermal. When you say Q dot is m dot CB delta T, that's thermodynamics, not heat transfer. This is the heat transfer. And so the purpose of this equation is to calculate the area. And the whole idea, or what are you required to calculate in this project number 4, is the area of the heat exchanger. Okay? But that heat exchanger is going to be a little bit complicated, because you're going to heat steam in that heat exchanger from hot gases. I guess maybe I should make the steam blue and make the hot gases in red. So the hot gases will come here at A and leave at B, while the steam is starting as subcooled liquid, then saturated liquid, then boiling at constant pressure, then saturated vapor, and then superheated vapor. So what problem do you see already? What problem do you guys see in this project? This is a heat exchanger. The cold fluid is doing this, and the hot fluid is doing this. Tell me, what problem do you see?
You're losing a lot of energy from the cold fluid going through the wet region.
You know, actually, I meant the problem for you, like solving this problem or calculating the area, not like system problems or design problems.
Where do you use delta T?
Which is delta T, right? Where is the delta T? So what we're gonna do is divide this into 3 parts, right? And so actually it would be the sketch for it. Remember this, because you'll ask me later on, like where do we start? We start like this. We start basically saying our hot gases are doing this, right? And then the superheater pipes is going to do this. This is the superheater pipes. And then this is the boiler pipes. And then this part, the last part, which now the hot gases are the coolest because they went through a lot of cooling. And the water is the coolest. This part is called the economizer. Economizer. Economizer, like it's very economical to use it. Why? Economizer. Economizer. the economizer. Okay, and what do they call it like? They call it like this. Well, they thought that if we heat the steam with something else before we send it to the boiler to boil, that save a lot of the fuel. That's very economical. This part is called the economizer, and the economizer was always the unit outside the boiler that heat using waste heat from other process, and then eventually became part of the boiler and so on. So the economizer is a part where the steam become HG, sorry, HF. And the boiler is the part where the steam become HF, and then the superheater is the one that take you all the way to the what? To the 1,000 degree, Fahrenheit or higher. Yes, question. Okay. Say that again. Sorry, yes, I'm sorry. HF and HG. Let me make it a little bit heavier. So this is HF, and then this is HG. Right. So this is really kind of a boiler. We are basically designing 3 coils for the boiler. Yes.
Just to clarify what they're called, so you got the
superheater,
the boiler, and the economizer.
Economizer.
Okay.
Coming from economy.
Yep.
Nobel Prize in economy, right? So the superheater, the boiler, and the economizer. And so the project is asking for this area, this area, this area, for each part of the coil. And so for each part, we need to know what is the delta T for that part so that we can use the one and only equation in heat transfer, which say Q is UA delta T. Okay, of course, the U is a big question. What is the U? You will have to assume a reasonable U in your design. Yeah, you have to find out what is a good value for that U. I'm not going to give it to you. It's a big deal. What is the right U to use? Okay, so each unit, Q is UA delta T, Q is UA delta T, Q is UA delta T. All right? Very good. The project look a little bit more scary than this, but it boiled down to this at the end. There's 3 units, each unit we just need to calculate there. Okay. So what is delta T? How we can calculate the delta T? Again, if the delta T is constant, then we have no problem whatsoever. It's the problem when they start changing on us, right? So by the way, here is what is that? What's in this table? U values, right? But for different heat exchanger. The U for a feed water heater, that's your U. Okay? Steam to light fuel oil. Okay, steam to heavy fuel oil. So those, but it's a big range, which is really annoying. Gas to gas, heat exchanger. Steam to air in fan tube. So you can see how the range is really big. All right, so this is the part about the steam, right? Q is M dot HFG. And now we are after this. Q is UA delta TM. That is the guy that we want. So this, I'm not going through this, but this is the derivation. This is the proof. This is the proof why the best delta T, or not the best, the accurate delta T to use between the hot and the cold is this. Okay. Why? He did it for a differential element. He basically said, let me just get a small element between the hot and the cold. Okay, and figure out how much the cold did, and how much the hot lost, and how much the cold did gain, and then let me at the end of the day find out the relation between the Q and that temperature difference. Okay, and so out of this derivation, out of those 5 equations together, when you solve all of them together, you figure that delta Tm is delta T1 minus delta T2 over ln delta T1 over delta T2. So personally, you know, when I was undergrad, I always tend to forget. Of course, you don't care because the exam is all in books, so you don't have to remember. But I mean, it's annoying always to have to check what was the formula. It's nicer if you remember a little. So I used to forget, is it delta T1 minus delta T2 over ln delta T1 over delta T2, or is it ln delta T1 over delta T2 divided by delta T1 minus delta T2? Of course, it is the first, not the second. So how do I not forget? What is the easy way for me to tell myself, you are silly? Of course, it's the first one. How could I tell my parents, what are you talking about? Of course, it's the first guy. Why? Why the first guy is correct and the second guy is wrong? I mean, depend on who's delta T1 and who's delta T2. It's the units. The units. You will be surprised how many mistakes you can figure out just by the units. What's the units of this formula? What's the units of this formula? Yeah, it has to be Kelvin degree C, because the guy at the bottom, what's the unit of the guy at the bottom? Dimensions, because it's delta over delta. So if I'm looking for logarithmic mean temperature difference, I'm looking for delta T. Of course, it should be delta T1 over minus delta T2. It cannot be the ln over the difference, right? So that's the first thing. The second thing that you may be confused about, delta T1 over delta T2 over the ln delta T1 over delta T2. Who is delta T1 and who is delta T2? I mean, in this, excellent. But let me give you my 2 minutes first before we get your answer. So in barrel flow, you would have an easy time deciding, because you would say, well, why would they call the inlet 2? I bet the inlet is 1 and the exit is 2. So you don't have problem in barrel flow. But in counter flow, when the hot is doing this and the cold is doing this, now you are not even sure, is that delta T1 or is this delta T1? Who is delta T1? And so it turned out it doesn't matter who is delta T1. I mean, we can do this as delta T2 and this is as delta T1. What is this? The difference, right? So like this guy is 90 and this guy is 50, and this guy leave here at say 70, and this guy is coming at say 20. So whether you're gonna make this 40, this is 50. Whether you're gonna make it 40, why my pen is so okay? Whether you're gonna make it 40 minus 50, or amazingly 50 minus 40 is gonna be the same. How is that possible? And ln x is minus ln 1 over x. So ln 40 over 50 is minus ln 50 over 40. So if you say 50 minus 40 and you have plus on the top, you will end up with ln 50 over 40. And it's plus. If you say 40 minus 50 and you have minus, you're going to get ln 40 over 50 and you get minus. So it's going to be the same. So, but I would say, let's just always make delta T1 to be the biggest difference so that we don't have to say negative or negative, because who knows, maybe you will forget one of the negatives. So let's not even worry about it, right? So I mean, when you see 50 and 40 on one side, you basically tell yourself the logarithmic mean temperature difference is the 50 minus the 40 over ln 50 over 40. Okay. Good job. So then the Q, if they ask us, so we are doing this problem so that we can figure out what is the area of that heat exchanger that is cooling the hot fluid from 90 to 70 while heating the 20 to 50. We will calculate this over the calculator, and then we would say the Q dot now is UA multiplied by that temperature, logarithmic mean temperature difference. And that will give us the area. Okay. Good. So this formula, it's complicated, but it's really good for calculating a correct delta T. Because see here, if you assume or if you think, I'm just gonna use why they are doing all this? Let me just use my average. You know, so what is the average? The average will put you here. Ouch. The average, that's not good. Okay, I think I can make a line, right? Which one make lines? Yes. So the average will actually give you this difference. And see, it's not really fair. Right? If you say I'm gonna say the temperature that I have is this plus this over 2 minus this guy. You are overestimating the delta T. And that will result in underestimation of the area, which is not good. You buy a small heat exchanger and you'll be surprised that it's not enough to send the same flow rate, so same heat transfer. Okay, so what we need to do is use the logarithmic mean temperature difference for accuracy. However, if the difference between this side and this side is not really that big, if the delta T1, delta T2 is very similar to each other, like small difference between them, you will be happily surprised that the average will do almost the same job like the logarithmic mean temperature difference. So the logarithmic mean temperature difference is always accurate, but it's not always required. A mathematical average will work as fine. So I mean, if you hit the ln or you don't have a ln in your calculator and you are running out of time, we can use a mathematical average if delta T1 and delta T2 are close. As a matter of fact, if the difference, I think I remember C is saying here, the mathematical average will work as long as the difference, I think, is like 40%. Look at that. 40% difference. You think that's too big? 40% difference. Like one of them is twice the other guy, more or less. And that will give you an error of 1%. So I bet if the difference is like one of them is 90% of the other one, you know, like one of them is like, 100-degree difference and the other one is 90-degree difference. To say that the average is 95, that will give you almost the same results as the logarithmic mean temperature. Okay, so always correct, but not always required. Make sense? Okay, so this definition of logarithmic mean temperature difference is only valid for barrel flow, which sucks, We said that last time. Should never do violent flow. And counterflow with shocks. Should always try to do counterflow. Right? This is really great. But for other configuration, like cross flow and cross flow and shell and tube, all those configuration, you cannot use this derivation on them. It's not like that. It's not like the hot is always transferring to the cold in the next step. The cold in the cross flow, the cold kind of like go and leave and come again, like he exchange with the hot side of the hot fluid and then come and exchange heat with the cold side of the hot fluid, just because of the way they're trying to pack a lot of surface in a small tiny place. So they do all those configuration. So for all those configuration, what happened now? We have to hit the logarithmic mean temperature difference that we calculated by a correction factor. Okay. This. You see that correction factor? This F here. That correction factor is less than 1. That correction factor telling you, you think you have 10-degree difference between your hot and the cold? No, you don't have 10. You have only 7. You have only 5. Because the way that you are sending the fluid through the... So how do I get my F? I get my F from a chart like this. What is this chart? Y-axis F. Ideally, you go to 1, but then it can be 0.9 or 8 or 7 or 6 or 5, depending on what? Depending on the x-axis, which is this, and the curve that you're using, which is this. Okay. What is capital T1 and capital T2, and what's small t1 and small t2? It's basically those guys. So each one of those charts has a key, and that key basically tells you what is the T2 and T1. So what is it? So the T1 is the inlet temperature of the shell, not the hot or the cold. You don't care whether it's hot or cold. It's the inlet of the shell. And capital T2 is the exit of the shell side. And the small one is the tube side, inlet and out. You put those numbers in, you come here to this chart, figure out what's R and what's P. You come in the right chart, read the number, 0.85. That is the F that you will multiply the logarithmic mean temperature difference with. Okay. Now the question is, of course, what is delta T1 and delta T2, right? And so it's basically this and this, right? So capital T1, capital delta T1, capital delta T2. Right? Why? Because they are so close together. They are like, this is the same side. Does it matter whether this is delta T1 and this is delta T2? No, it does not matter. You can swap. It's not a big deal. But it's like when they come together, that is one side. The other side will be the other. Right? You wish, and if they are smart, they will let this guy come here. And this cartoon is probably wrong. This T2 need to come out from here. Right? Why it need to come from here? Because it will be kind of like trying to approach, if they get T2 out of here, why that's good? Ouch. Why? If this was T2, that would be better because it would be as if counterflow, right? You get in while this guy is leaving. You hit your hottest point at the inlet of the hot with the hottest point of the cold. So you're doing counterflow. All right. Point of the story, to get the correction factor, we need to use those charts, depending on, do we have one shell, two shells, and we follow the recipe exactly to get the P and the R and get the F. Once we get the F, we are back into the equation. Where is our equation? This equation. Q is UA delta T. Delta T, this multiplied by that. Right? Let's take our 15 minutes break and we'll start again at 6:05 or 6:03. I think we should start, guys. So people online, can you confirm you can hear me?
Yeah, I can hear you.
Thank you. All right, so I wanna spend 2 minutes on this. So there is something called SME. What does SME stand for? American Society of Mechanical Engineers, right? And there is AIAA, which is the American Institute for Aeronautics and Astronautics. And so when you become a professional engineer, it's nice to be a member of those society because it shows you what's going on professionally and stuff. And so in Tulsa, we have a professional section, it's called the Mid-Continent section. It used to have this jurisdiction over all the way from Dallas to Kansas to Louisiana. All this was the Mid-Continent section, and it was headquartered in Tulsa. We used to have a lot of oil and gas. That was the place for engineering. And then under that professional section, there are 3 student sections at ORU, at TU, and at OSU Tulsa. The student section here started in 2001. Okay. And so the professional section, they do their monthly seminars because they're engineers. There's something called PE degree. In order to be a professional engineer and be able to sign drawings and stuff, you need to maintain your professional registration, professional engineer registration. And that you need to require something called professional development hour. So they have to continuously educate themselves. So they're still up to date with the technology and stuff. So that's why they need to do all those seminars. And so we as student section, benefit from those seminars because like say student in Stillwater don't have a professional section with them. So their SME section is basically restricted to things that is offered at a campus, university campus. But here we are really lucky that we have a professional section that gives you good connection. I mean, when you go to seminars, it gives you good connection to people actually working in industry so that when you start looking for jobs, those will be people that will be useful for you. I also would like to say that when I came here, I became assistant professor here in 2003. And so at the beginning of the year, the dean of engineering basically have a faculty meeting where he bring all the faculty and the department heads, chemical and mechanical and electrical, and every department head stand up and he say, who are the new hires? Who did they bring this year over? And so at that year, my department head stood to introduce me to the rest of the college and say, we got this guy, he came to Michigan. And I have his resume over here, and he was the student chair of that student organization. Out of all my resume, and I have a bunch of awards, in my resume, the thing that grabbed his attention was I was a chair of a student organization. So all this, I'm trying to tell you that I know that you are all busy. I know that it's amazing that you are actually in the class in the first place. And that every single day you are like saying to yourself, it's amazing I'm alive with all the things that's going on. The good job, I'm still here in this world. And you don't have a minute to spare. But that's why when you become involved in those student organization and in your resume, say bachelor degree, and here is my skills and here is my experience, you also say extracurricular activity and you say, I was the student chair of the American Society of Mechanical Engineers. I mean, that told them that you are really, really good time management. Not only you are working full time, and some of you even have family, and you get your bachelor degree, and you also were a student leader. So it speaks tons of things about you, and it's not as time consuming as you would think. Okay, it's not as time. Basically, you probably, if you are the chair, which is really the only one who work, everyone else just sit on the table. You just run a meeting every month, and you have a professional section that's already organizing things. All you have to do is just like ask your member to go and attend so that they can learn a little bit more, or make this particular course, or like you are basically directing activity from the headquarter or the professional section to the section. Okay, so I'm almost done. So we, for the first year, and I've been the advisor of the SME section since 2014. So that's like 7 years. I know we are all under the weather with COVID and all the stuff, and you guys are just about to graduate and you don't have time. But for the first time, we don't have anyone to volunteer to be the chair. There is one person that volunteered to be vice chair, one person to volunteer to be the secretary, and we still need a treasurer and a chair and a liaison to the professional section. That's the one that will attend the meeting of the professional section. And it used to be like you need to go to PSO. That's where we had the professional section meeting, you know, in 7th Street, I think, or 6th Street, the PSO Oklahoma, the electric company of Oklahoma, Surface, that's where we used to have, but now it's all under Zoom. So basically you just log in your Zoom 1 hour, lunch hour on Thursday every month. Okay, so please think about this because it looks nicer in your resume. It does not take that much time. Okay, and you make, again, I will finish by this because we don't have that much time. A lot of people think they are in college for the degree. Yes, you are in here for the degree, but you are also here for what's the second most important thing that you get from a college education? The network that you build. Those people sitting around you, hopefully a few of them will be successful, and they will be the one that will tell you about your second job. Maybe if you are looking for a, like after you spend an average American changes their job every 7 years. So when you are looking for the second job, he or she will be very successful running their own company. One of my schoolmates actually just last month was awarded $73 million contract for his company. Okay, so that's the network that you want. You want successful people around you that can, you know, not give you jobs, but you need them. And in this campus, the only thing that I admire every one of you, the fact that you work full time and you come here and after a full-time job, you come and listen to me for 3 hours, that is amazing. You know, that shows perseverance, it shows that you're committed to your career. But what I hate about this campus is that by default, after the 3 hours, you just leave because you cannot wait to get your lunch or dinner and check your kids. And so you don't spend the time hanging around with each other. And that part is missing. And being part of a professional society, whether at the student level or the higher level, you make that connection. I mean, it's not, what's your name? So it's not enough to say, I know Steve, he was sitting next to me in the class. Well, maybe at night he's a serial killer. You don't really know him until you start volunteer with him in activity. And you say, you know what, Steve was really very dependable. I know I will recommend him for any job because when we were serving on that thing and we wanted someone to put the flyer or go to the student fair, he volunteered and he did an excellent job. So we need more connection on this campus compared to the regular section. Because in the regular campus, they just live together in the same campus. They eat together in the same room. They hang around for 4 years together, so they really know each other. But here we just meet in the room while you are half asleep after a full-time job, and you just cannot wait to go home. So the extra, and it's not that much, but the extra time that you would put in those society, and most of the time now it's all by virtual meeting, you will take your relation to your colleagues a little bit up. Okay, and that is very important besides just your education and network. Strong network, people that you worked with and you know them and you can recommend them and they can recommend you. Okay, all right. So end of the day, here is a Zoom meeting. It's under announcement. Okay, under announcement, you will see where's how can you log into this is the professional section seminar this month. Okay, and you will learn from seeing what people are actually working on, so that helps you decide your career later on. Maybe you'll think oil and gas sucks. I don't want to work for them. I want to work in aerospace. Or maybe the opposite. You'd say, I don't want to work with aerospace. Those people are doing nothing. I want to work with oil and gas. So it's nice to see what they are actually doing. I know also a lot of you work, so you have first-hand exposure to, but still, it's nicer to see what else is going on outside your own career. Maybe there's something even more fun outside the company where you work at, right? Okay, questions about this, comments? All right, very good. So, heat transfer. Q is UA, logarithmic mean temperature difference, for counterflow and barrel flow. For any other configuration, shell and tube, double shell, and you look here at this double shell, it has to have, they will tell you it's 2 shell and how many bypass? 1, 2, 3, 4. Well, it could also be 1, 2, 3, 4, 5, 6, 7, 8, right? I mean, it can be 4 or 8 or 12. You can add more tube pass inside each shell. Whatever, as long as it's 2 shell, you will use that chart. You use that chart to get the F, right? This is the penalty for having. I mean, then you ask yourself, why then I would use it if they have smaller, like the logarithmic temperature difference is now smaller because I hit it with an F, which is 0.8. But what is the benefit of doing this? You back more area. So yes, the delta T is smaller, but the area is way bigger, right? In the same volume. So what I'm saying is that, I mean, you are sad because you are multiplying by that F, right? And they say this F is like 0.8, but you don't realize that this area now, because you just use this configuration, is way bigger than if you have used like just regular counterflow. Okay. One question: How do we go about volunteering? So if you wanna be running any one of those chairs, you just need to be a professional, not professional. You need to be a student member of SME. So you go to sme.com. I mean, you can just Google student member of SME, and you will get here how to join. And join now, and it's $25 per year. But the professional section, to improve the student membership, they will pay $10. So you only pay $15. So every one of you is losing $10 right now. Not more. Okay. And so once you enrolled and you have a number, you email that number to me. I'm the advisor of the section, and you tell me I want to be the chair. And if we get 2 chairs, we make an election. If we have only 1 chair, then we are done. Here's our chair, here's our vice chair, here's our. So I'm telling you right now, we have an empty slot for a chair, an empty slot for the liaison to the professional section, and an empty chair for the treasurer. Just the secretary and the vice chair. Basically, the 2 jobs that hardly do anything. Those people, those are smart students. They said, we're just gonna get this title, put in our resume, we are done. We don't do anything. So, all right. So we will just use those charts, huh? Some of them are a little bit confusing. I think we said that last time. Like, for example, this Huh? This is cross flow. This is car radiator. This guy going this way, this guy going that way. And sometimes they divide them into pipes and passage. So then they tell you both fluids are unmixed. And sometimes only one is mixed and one is unmixed. And of course, you would follow the recipe. So T1 would be the one that is mixed or unmixed, the small T1. This is the mixed or the unmixed? This is the unmixed, right? Because you go into passage, it's unmixed. But T1, the capital T1, this is mixed, like they all go as a, let's go together. It's a stampede of fluid. Everyone run. There is no hole, there is no passage, there is no tubes to go through. Okay. So let's look at this example. Water is heated by steam condensing in a condenser. Good. Here's the water and the steam. And he wants the required length of the tube. He's basically asking for the area. The length of the tube is part of the area. If the heat exchanger is a counter flow like this, what would be the heat transfer area? Is it pi over 4d squared or is it something else? It's the surface area. It's pi d L, right? So if we get the area from the heat transfer equation, Q is UA delta T. Q is UA logarithmic mean temperature difference. We get that area, then we will tell ourselves that area is pi dl. And am I going to use an F or the F is 1? Should we use F or the F is going to be 1 here? I can't hear. F is 1 because this is counterflow. So counterflow, barrel flow, F is 1. The equation was created for them. It's the other guys that require an F. Okay? So you notice that we need the 4 temperature to be able to do this. In order to calculate the logarithmic mean temperature difference, in order to say delta T1 minus delta T2 over ln delta T1 over delta T2, we need the 4F. So the 4 temperature. So this equation or this method is perfect when you know all the temperatures. Then it's a piece of cake, right? Okay, so let's see what we got. We got all the temperature, and we also have the CP, right? Of the water, and we know the m dot of the water. So do we know the q dot of the water? We know the q dot of the water, right? Because it's m dot CP delta T, right? So I have my counter flow heat exchanger like this. And he's asking for the area. Required is the area. And the solution is Q dot is UA delta T logarithmic mean temperature difference. So delta T1 minus delta T2 over ln delta T1 over delta T2. So I'm gonna say this is my delta T1, and this is my delta T2, right? So watch. This was 20, and it leave at 80. See, and the steam come at 120 and leave at 120. How is that possible? How is it like he does not change his temperature?
It goes from a gas to a liquid.
Yes, it's constant temperature phase change. Exactly. Exactly. I mean, if we want to plot this, it will be something like this. That's the hot, and the cold is doing this. Coming from 20 all the way to 80. right? While the steam is basically condensing at 120, right? So 120 minus 20 is 100 degree, and 120 minus 8, that's 40 degree, right? So I would call the delta T1, and the Q dot, by the way, is we will get it from M dot cold, CB cold, delta T cold. That's the water side. UA, and then you got the 100 minus the 40 over ln 100 over 40. Okay, so, and the U was given, right? I mean, it has to be given. There's no way we can get the U. I don't see the U. How is that possible? Yeah, it's given, but not in that particular sheet, but it was given. He said the overall heat transfer coefficient is constant and usual. So he gave it to us. I just don't see it. All right. So if this Q is given and U is given, then the only thing that you can find from here is the area. So find the area, and it's going to be by dL. You will be able to get the L out of this. Right?
So we would need U.
We definitely need U, because otherwise, how are we gonna calculate it? But I guess I copied the solution without copying the problem statement. So if we open the book, this is from Gajar book, not the MIT book. I bet you see this part, in the assumption the heat transfer coefficient is constant and uniform, they actually give us the value. Okay. This one, this is a shell and tube. Okay. And I guess what's important in this guy is to realize where is the delta T. This would be the delta T. Because again, at the same port, right? And it's okay to call this delta T1 or delta T2, and this is the other delta T. So like when I leave from one place, I mean, I put my hand and say, this is the delta T at one side, and the other guy would be the other side. So in this problem, he said the surface area is to be determined. He wanted the area again. No, sorry, he wanted the U in this problem. During experiment, the inlet and exit temperature of water and oil were measured. The overall heat transfer coefficient based on the inner surface area is to be determined. So, same equation, Q dot is UA delta T, but now there's an F. Why there's an F? Because this is not counterflow or parallel flow. This is shell and tube. We need an F from it. We need to use a chart for shell and tube. One shell, and we don't care how many tubes are, right? I mean, if I go back to the chart for shell and tube, it says this is one shell and 2, 4, 6, 8, whatever. It doesn't matter how many tube bars we got. Right? So then I just need this and this, the shell side, the tube side and the shell side. And then I'll come here and fill in the blank and find out what's my R and what's my P. P is the x-axis, R is you see R is the curve. Make sense? And that will tell us what's there for that shell and tube. Okay, so we will get the F, this F, we'll get this F from the chart, right? And this delta T, we got all the temperature, we can get it, right? And the Q dot, you can get it from the cold side, because again, he told you he told us what? He told us the flow rate of the cold 3 kilograms per second, and of course the CP of the water. So you can get this Q dot. Okay, so the only thing that's unknown is the U. So what is with U based on the inner surface area? What is the deal with that? What does it mean? Anyone? Why they call, what difference does it make U based on the inner area or U based on the surface, an outer area? So when you say Q is UA delta T logarithmic mean, this two guys could be U in area in or U out area out. Okay. So the pipe that is separating, say the hot fluid that's going on and the cold fluid that is around on outside, has two diameters, right? So when we said the area is by DL, is it by D out or by DL? So UI, DI will be the same as U out. DI is the same as U times ND. So when you want the inner area or the inner, the U based on the inner area, you just have to use the diameter, the inside diameter of the pipe. Okay? And the same thing if you want the outside area, you just use outside of the pipe connecting the hot with the cold. Make sense? Good. So this method is easy. I loved it when I was undergrad, actually. But this method sucks when what happened? When you don't know the four temperatures. Most time when you know two temperatures, that are the problem that you will face. So, for example, they will tell you here is the hot fluid coming in, and here is the cold fluid leaving, and we are wondering what is cold TC out, what is it, and what is T hot out. We don't know those guys. And they will give you the U and the area. And let's say it's even counterflow. So no problem for that. Now, what is the problem? Well, okay, I'm going to write Q dot is UA delta T logarithmic mean temperature difference. Okay, I don't know the Q dot. I know the U and the area, but I don't know the delta T. So why I don't know the delta T? Because I mean this side, I don't know this guy, and this guy, I don't know this guy. So that's why I don't even know how much is Q dot hot, and I don't know how much is Q dot cold either. Right? Because I mean, how can I get my Q dot? I need to say it's M dot CP delta T. Well, that is not really known. So when two temperature is not known, the logarithmic mean temperature difference will involve try and error. You will have to assume what is the temperature and go and check, is that will this temperature make the Q equal the Q or not? You can imagine the procedure, right? You would assume, well, let me assume it will go up to 50. Okay, if I know that's this 50, then I can calculate this, and then I can calculate this, and then I can go and use this equation and see does really 50 make that happen, make this like 90 happen or not. No, it didn't. Let me go back again. And you iterate and iterate and iterate. So for those scenarios where two temperatures are not known, It's either you know all the 4 temperature or you only know 2 temperature. Because if you know 3 temperature, then that's good enough to get the 4th temperature. Because you would say Q equal Q, right? So if you know 2 hots or the 2 cold, you'll be easily say, I know that this heat exchanger have this much Q dot. So if he's losing 5 kilowatt from the hot, I bet the cold will get those 5 kilowatt because we always assume very good wrapping, very good adiabatic sealing at the end, right? So for this scenario where 2 temperatures are not known, we move to the effectiveness method. And as I said last time, I hate this method when I was undergrad because of all those like weird equations. I was always worried that I don't have time in the exam to do all this. And also I was worried that my eye will not get all the number right. But the good news is charts. There are charts that you can use. And there are a MATLAB code that I'm gonna post it for you, if it's not already posted, that will allow you to use this, just like we use the XTeam and we use the psychometric chart on MATLAB, we will be able to use that effectiveness method on MATLAB very easily. So that makes it very popular then, right? So we don't have to be scared of this. We'll never really use them ourselves. We will just tell MATLAB, use cross-flow, use shell and tube. We tell him the heat exchanger and he will calculate. So what does he calculate? What is this effectiveness method based on? It's based on this. This is the bread and butter of this method. The effectiveness is Q dot over Q dot max. He actually should have called it Q dot actual over Q dot max. Epsilon is Q dot over Q dot max. Okay. So of course this Q dot, as you can see here in the slide, this Q dot is both the Q dot hot and the Q dot cold. It's the same Q dot, right? So knowing that Q dot, you basically know the Q dot hot and the Q dot cold. And so if we, again, why do we use this method if we don't know the 4 temperature? We only know TCN and THN, and then you say, that exchanger, you think how good he is, how much he will cool the hot fluid, how much he will heat the cold fluid. So you go into this method to calculate the Q dot actually, right? So you are using it so that you can tell what's Q dot, so that you can come here and you'd say, therefore, that is my TC out because I know the Q dot. What is this capital C? Yeah, it's M dot CP. Out of all the alphabet in the world, we just use another C for it. Okay, so we got M dot CP is equal capital C. Right? So the capital C, the heat capacitance kind of the heat exchanger is M dot CP. Right? So here he's explaining to us what is capital C cold and what is capital C hot. Right? So epsilon is the ratio of Q dot, actual Q dot, to the Q dot max, the dream, the dream of the heat exchanger. So the dream of the heat exchanger is if this is T hot in and this is T hot out, and this is TC in and this is TC out. We said before that the dream is to make why? this delta T max. Delta T max between TCN and THN. If he can make one of them do that, that would be the perfect heat changer ever. He made the impossible possible. He managed to make the TCN get at the end as hot as THN. I mean, you cannot wish for a better outcome than this, right? And that, of course, requires how much area? Infinite area, right? So ideally, that will not happen. But that is the dream. That's like, you know, like it's Carnot cycle, kind of. I mean, you're not going to hit Carnot cycle, but you tell yourself how far I am from it. All right? So the guy that will be able to do this, huh? I mean, this dream can also be realized by what? By this. I mean, maybe the hot will also get as cold as, right? I mean, so TH1 can get to TC1, that would be a dream, or TC1 can get as hot as TH1. At both scenario, you will have delta T max. But which one will do it? Will the hot manage to do this, M dot hot, C hot, do this, or will the cold, M dot cold, C cold, manage to do this? And it turned out that the guy with the minimum M dot CP is the one that will be able to achieve this, because the other guy can supply that for him. Okay. So in order to find out Q dot max, it's not just delta T max, it's delta T max multiplied by M dot CP minimum. So you start the problem by figuring out which one is the minimum. Is it M dot CB cold or M dot CP hot? So really, this is a step one to figure out who is the minimum. And then step two is to say to yourself, then Q dot maximum will be the minimum of those guys multiplied by delta T max. And then step three would be then Q dot actual is Q dot max that I just calculated multiplied by epsilon. Okay? And epsilon will come from all those chart equations. All right? That's the procedure, basically. This comes from charts. And so once you did this and you calculate this Q dot, then you tell yourself, okay, M dot is M dot CB cold, TC2 minus TC1. And it also happened to be M dot CB hot, T hot 1 minus T hot 2. And that allow you to get the TC2 that you didn't know and the TH2 that you didn't know. Okay, makes sense? So we figure who's minimum, we calculate what's Q dot max, and then we calculate Q dot, and then from Q dot we calculate what? We calculate TC2 and TH2. So obviously this method is really convenient to calculate temperature. But in order to be able to calculate this epsilon, you need to know the U and the area. So really this method is if you have a heat changer sitting in there, you're not designing a new one, you know the U and you know the area, and he's telling you, I'm going to have this hot fluid and this cold fluid coming in that heat exchanger. What will happen? That method will do that for you. The other one was if you know the temperature that you would like to achieve, what is the area required? How big is my heat exchanger? Okay. So let's see those charts and how we can use UA to calculate epsilon. right? So it's not really scary. I don't know why I was so scared from it when I was undergrad. So, so by the way, the epsilon, of course, as we said before, epsilon is Q dot over Q dot max, right? Which happened to be Q dot actual over that dream. Now he's saying, well, that dream could happen by the cold, or it could happen by the hot, depending on who got the small capacitance, heat capacitance, who got the small m dot Cp. So if he's saying if there's the hot, then you can write it like this, and you can write it like this if it's the cold. See how he's using Q dot from the cold, and here he's using the Q dot from the hot. He can, but the Q dot max could be either the cold or the hot, depending on which one is many. And so the formula for epsilon can become like this or like this. Okay. So what is nice, of course, this guy, you see a typo here, right? What this should read, guys? This should be THN, right? So fix this in the notes. This should be, ouch, THN. Ouch. So this should be THN minus TH out. Or TC out minus TC in. The bottom is always THN minus TC in, which is delta Phoenix. Anyway, so how we calculate the epsilon again? Show me the epsilon. So here is the equation for epsilon barrel. Okay, and so that equation for epsilon barrel, 1 minus e to power UA, that's UA, over C menu, plus 1 over C menu over C max, over 1 plus C menu over C max. So all the formulas, always you'll see that the ratio, they have the ratio C min over C max. So C min is either the hot or the cold, and C max is either hot or the cold, depending on which one is smaller. But the point is that you will see that ratio in the formula. And you will see that over and over. And you will see this, UA over C min. So to make the formula a little bit smaller from our eyes and from the computer, they have a name for this and they have a name for this. I mean, they could have left the equation as they are, but it just makes sense to make it smaller, and also because those things physically mean something. So the first thing is UA over C min. UA over C min is called number of transfer units. Okay, UA over C min is number of transfer units. And when you think about it, this is really the guy that tells you how good or how close your epsilon is compared to 1. Because as this number increase, UA over C min, what happened to that term? It approach. Imagine if UA over C min is infinity. E to minus infinity is 1 over e to power infinity. What's 1 over e to power infinity? 1 over e to power infinity is 1 over infinity. What's 1 over infinity? 0. So this become 1 minus 0 as UA become infinity. Makes sense. If UA is infinity, and by infinity I mean like 10. It doesn't have to be to go to even thousands. If UA become bigger and bigger, especially UA over C min, that's the real difference. If UA over C min become big, then you have a lot of error, or you have very good U. They made this thing moving with very fast velocity that the U over only transcription is so high. Or C minimum is small. What does it mean? The m dot Cp is very small. So that fluid that you are trying to heat, he got so much, like his m dot and Cp is so small that you give him 10 joules, it's like, yay! and his temperature shoot off the roof. Because his m dot Cp is nothing. Huh? He's not really that greedy. I mean, his m dot Cp is just like, you know, one Kelvin or something, 1 degree. So m dot is kilogram per second, and Cv is kilojoule per kilogram, Kelvin. So you multiply the two of them together, and you get what? You get kilogram cancel, and you get watt per second. Watt per degree C. So you give him this many watt, and his temperature go over the roof. All right? So number of transfer unit is U over Cmin, and the Cmin over Cmax, again, out of all the letters in the world, they decided to also call it C. This time a small c. So we have C sub B, that's a acidic heat. We got C minimum and C max, and C cold and C hot. And then we have small c, which is the ratio. And in some books, they call it CR, C sub R, which is the ratio between C minimum and C max. So then this equation, at the end of the day, is function of two things: number of transfer unit and the ratio. So the MATLAB code that you will find it posted on our canvas. Like the X team, we used to give him H and T and tell him, give us the pressure or give him the entropy and give him two property and ask for the third. Well, this one, we give him two property, which is NTU and the small c, and what kind of changer it is, barrel counter, shell and tube, and he calculates stuff for us. He calculates epsilon for us, basically. Okay. So look at all this. The formulas now are a little bit nicer, because I mean, imagine if you didn't plot or didn't write NTU, it would have been, and the small c, you know, it would have been so messy. But those are the equations, right? And those are the charts for them. So here is the barrel, here is the counter, here is one shell, here is two shells. Okay. The x-axis, the y-axis is always effectiveness. And you can see you can hit infinity. So when NTU become infinity, which turned out to be like 5, that's our infinity. Okay. When NTU go to infinity, you get effectiveness equal 1. Right? Infinity 1. Effectiveness is 1 when the number of transfer units like become 5. Okay. So now for this parallel flow, there are all those curves, counter flow, all those curves, shell and tube, all those curves. What are those curves for? C minimum over C max, 0, 0.25, 0.5, 0.75, 1. So what do you notice on those 4 graphs? There is also the other 4 graphs, the other two for the cross flow, right? So what do you notice? Something very important to notice between those should grab your attention. For a free quiz, tell me something interesting that you see. Anyone? Ouch. Can't hear with your voice. They always have the same shape, but are they always the same value or they go to different value? They go to not slightly. I mean, this guy go to 50, this guy go to 60, this guy go to 70, this guy go to 80. Right? They are not, except for one curve. This guy is exactly the same curve for all of them. So now the free quiz is to tell me why this curve is always the same for all of them. You tell me the physical significance or the physical explanation, why this curve is the same no matter whether you are barrel, counter, cross flow, why? That is for specific heat of water, and why water would be the same no matter what. No, that's not true. Water is just like any other fluid. No, it's not water. This curve belongs to, and that's why it does not matter whether it's barrel or counter or shell and tube, they only perform the same. So you have to say what this curve represents and why this doesn't matter. The configuration, you will always do the same. Free quiz. 2 quizzes. Yes, exactly. The top curve of all those configuration, those 4 and those 2 guys, that top curve is always the same. He always, like when you hit at 1, he will read the same number. When you go at 2, he will read the same number on the y-axis. That's different from all the other curves. Like for example, the lower curve, you can see how it's different if you are barrel or counter or shell and tube. But the top curve is always the same everywhere. Whatever the configuration, same relation between the effectiveness and the ATU. Why? I can't hear. You want, what did you say? Okay, which one you want to zoom in? Okay, let's go to barrel flow. It's a good notice that C minimum is 0, but you didn't explain what is this curve represent and why it doesn't make a difference. You just read the chart for me. That is not free quiz. Free 2 quizzes, no. I need more. Give me more. It's cold to hot. It's always, the heat is always moving from the hot to cold in all of them. Every one of those curves are the ratio between Q dot over Q dot max. And Q dot become Q dot max only when you hit the 100%. So I mean here, when you are like 0.6 on that curve, doesn't mean you get Q dot max yet. It's only 60% of it. If you want to get Q dot max, you need to go all the way to 5, more or less. Then the top curve will go to 5. But my question is, why this top curve here in barrel flow is the same as counterflow, but the other curves are not. Like the 1 is not the same. The 0.25 is not the same. Only the top curve is the same. I'm gonna give you 5 seconds. Yes. Say that again louder. At 100%, the temperature is the same. No, the temperature is not the same. Otherwise, there is no heat transfer between the hot to the cold. So I'm going to, not just high, it has to be infinity to get to 0. So what does it mean? Again, you are just reading the number from me. I want more physical interpretation to this, but you are in the right track. This curve represents C min over C max equals 0. It's either C min is 0 or C max is infinity. That's how you get this ratio equal to 0. So what does this represent? And why it does not make any difference whether you sending this scenario in a barrel or counter or cross, it will always do the same. So if you explain to me why it doesn't make a difference, you get your 2 free quizzes. Why does it make a difference if there's a phase change? You're that close to get 2 quizzes. Yeah, I'm gonna get my 2 free quizzes.
Would it be because there's already enough surface area so the temperatures
Because
are
there's
equal
what?
each
Say that
other?
again?
Is it because there's already enough surface surface area through the heat
No, it's
exchanger?
not because there's enough surface area. Here, so C min over C max becomes 0 if M dot C minimum, if C minimum is 0, that's not the case, because then we don't have a flow, we don't have a heat exchanger. Or C max is infinity. When will C max be infinity? When delta T is 0. When delta T will be 0? When the other guy is going through phase change. So from the start till the end, his temperature is constant. So while the cold is doing this, the hot is doing this. So when you say Q dot for a phase change, what's Q dot? M dot HFG. But if you want to say, no, I want M dot CP delta T, I want to calculate it like this. I need my CP because, or my capital C, because I need to use this chart. Then in that scenario, you will have to say that my capital C is equal to 0, sorry, equal to infinity. Because you are saying Q dot is M dot HFG, right? Because you are basically doing this. Here is your TH1 and here is your TH2, right? While the cold is doing this. TC1, TC2. So then that means if I insist on using M dot CP hot, delta T hot, I mean this is 0. So then this has to be infinite. Okay, so now I would like you to imagine a case where you have shell and tube, where the steam is coming in at 100 degrees C and he's leaving at 100 degrees C. And compare this with a counterflow where the steam is coming at 100 degrees C and leaving at 100 degrees C. Or two shells where the steam is coming at 100 degrees C and he's leaving at 100 degrees C, while the cold is basically doing 2 bars and 2 bars. In all those scenarios, the cold fluid go into the pipe, and during the whole journey, whether it's parallel or counter or cross flow or shell and tube, what does he see on the other side of the pipe? Same temperature everywhere. Huh? It's like going into one of those haunted houses and it's always dark. And like no matter where you go, it's always dark. It doesn't really matter what's going on. It's always dark. So the cold flow is going, and man, what really matters is the area. I don't care what is my configuration. Just tell me how much area do I have to do, how many pipes, how many meters of pipe do I go to, and it doesn't matter how they are arranged. It's always 100 degrees outside. Right? So because of this, when you have phase change, I don't even have to tell you what kind of heat exchanger it is. It's the same equation, right? C min over C max will be infinity. So you just calculate NT over the number of transfer units 3. You just come here, and read the effectiveness. So the effectiveness is just function of the surface area and the flow rate of the other fluid, the C min, the cooling fluid, right? Okay. So then when you are working for a power plant designing a condenser, they will, like, it doesn't really matter whether you're going to make it parallel flow or counter flow or like shell and tube. It doesn't matter. What matters is how much material, how much surface area we have between the two of them, not the configuration. Because everywhere is just like 100 degrees. Right? So when we see this, what is going on? So when you see in the books, usually when they do the heat exchanger under the turbine, you will see them making the pipes like this, right? And you see baffles like this, and they will show you like the steam is basically condensing like this. You shouldn't be sad and say, man, they should have done counter flow. What a loss. No, it doesn't matter. Because everywhere outside those tubes, it is 100 degrees C, assuming he's at room pressure. Of course, no, he's not. He cooled down at or condensed at 0.07 bar, right? Which is at 0.07 bar, then the temperature will be what, 39 or 40 degrees C, more or less. Good. Questions? Okay. So now for the rest of those guys, again, we come with the x-axis, read our C min over C max for regular fluid now, hot fluid cooling and the cold fluid heating, right? We get the ratio and we read the effectiveness. And that book that from MIT that I put the link for you, they have amazing number of problems on heat exchanger, all solved problem. You can basically solve as many as you want to get ready for the midterm, right? So now this part is a little bit confusing, right? This curve. So this one is not confusing, right? So this is when both fluid are unmixed. That's easy. Both of them are unmixed. Every one of them go into pipes, right? Sorry, the opposite. No, correct. See, that's why I already got confused. Both of them are unmixed. They send both of them into passages or buffers, or like they're moving between walls. So that's easy. You just again find C min over C max and another transfer unit, go up like this, read your thing, and then read your effectiveness. The confusing part is this. So they, I guess, to save on graph or what, I don't know, they tell you one fluid mixed and the other is unmixed. Okay. And so obviously one of them is mixed and the other one is unmixed. So the unmixed is going in pipe while the mixed one is just like stampede together. So that's the part that's confusing. So C mixed over C unmixed, 0 and infinity, we lost on the same graph. Then what's confusing is, so which one is the dotted and which one is the solid? Which one? Like 4 and 0.25, right?
Dotted line is the mixed.
Say that again.
The dotted line would be the mixed.
Say that again loud, I'm sorry.
The dotted lines are the mixed.
The dotted line is the mixed. And why you are saying this? So C mixed over C unmixed is 0 or infinity. So the problem is see, this should have been C min over C max. So when C min over C max is 0, C over C max is 0, we come over here. So it's not, I mean, we reach this curve. When do we reach that curve? When one of them has a phase change, right? When one of them has a phase change, then we reach this one. So the question is, which one of them is actually is doing this? So he's saying the C mixed over C unmixed is either 0 or infinity. But this, in both scenarios, what happened is the C minimum is going to be, or C max is going to be infinite. That's why you are sitting over here. All right. So what we can, how can I decipher this for you guys? Well, the easy solution is not to come up with, we don't have to use this chart, then our life would be easier, right? But It's basically, you can see this guy is going to 1, 0.75 to 0.5 to 0.25 to 0. Okay, while the solid one is going from infinity to 4 to 2 to 1.3. Okay, so they all go from 1 to this curve. One of them is dropping, the solid one is dropping from 1 to 0.75 to 0.5 to 0.25 to 0. Okay, and the other one is actually increasing from 1.3 to 2 to 4 to infinity. Right? And so, again, this one is super easy. This is, both of them are basically having exactly the same one. And this one is, one of them is doing phase change, and it doesn't matter which one is doing phase change. Whether the steam is on the outside or the inside, it doesn't really matter. It's basically those guys. I don't remember how do I actually tell them apart. Like, for example, over here, 4 and 0.25. Is it the C mixed that is 4 or the C mixed 0.25? I don't know. I will have to check and come back to you. I don't remember. And it's really confusing. Yeah, we can solve some example. There is example of that. Yes. I actually would say the car radiator could be an example of the one fluid is mixed and the other fluid is unmixed. What does the car radiator look like? The hot fluid, the oil, the cooling fluid coming from the car is going into one pipe. And that pipe go back and forth, but it's one pipe. So that is unmixed. No, that's mixed. The one pipe flowing in one pipe, that's mixed. The whole thing is going in one pipe. And how does the air look like? The air has to go through those fins. So the air split and the hot fluid is not. So the car radiator will be, here's the hot pipe. And the air has to split to go between those plates. Right? So the air is unmixed, right? While the oil or the cooling fluid of the engine is mixed. Because you send the whole thing in one pipe. Make sense? Why the water is going into a pipe as a bulk? Is that mixed or unmixed? It's mixed with itself. Like, so the fluid is mixed with itself. You don't separate the fluid into passages. So if we have the coolant coming from the engine and we split it into tubes, okay? So all those tubes, and we have baffles for the air to go through. Now the air is unmixed and the liquid, the hot fluid is also unmixed. You unmix it. But if you say, no, go together, guys, just like one big pipe, we are not gonna make a bunch of pipes, just one pipe and let's send the fluid through it. Then that fluid is mixed with itself. Yes? Good. So, so this is the curve that we were talking about. So that curve, when one fluid is doing phase change, it doesn't matter what configuration, it's one equation for everything. epsilon is 1 minus E2 minus NTU. Very simple. What is that? C equals 0. Why? Because C max is infinity. Okay. Good. So let's take a 5 minutes break, and then we will discuss the projects, next projects, what we're gonna do with it, and how we can use all this information to solve. So 5 minutes, short break. All right. People online, can you confirm you can hear me? Yes, all right. So during the break, one question was why in those graphs, some of them don't start or don't go beyond 0.5. When the number transfer unit, those graphs finish here. Why is that? Why? Anyone? Why does graph finish here? No, it's just like if you continue, they would have painted this red. They get so close together, they are just like really red, right? And practically speaking, like why would you use a heat exchanger that have 50% effectiveness? That sucks, basically, right? I mean, this would be really tiny heat exchanger, right? You need to pick it a little bit. So no, all of them could have gone all the way to 1. All the equation should go to 1. It's just like they get so close, there is no point in painting them, right? I mean, even this one, look at this. You just like stop it here because you will just like need exactly the same curve, more or less. All right. So this is project 4. It looks so massive, but really what the new part is this. The new part is this. What is that? That is the heat exchanger. This is a boiler, a heat recovery boiler, where what happened? The hot gases from this cycle, this is the gas turbine cycle. The hot gas from this turbine is so hot, we shouldn't throw it away. That's a lot of money to be thrown away. They take that and they send it into a heat recovery boiler. So that those hot gases is enough to basically run the cold water here into superheat steam that can run a steam turbine. So, and if it's not enough, if those hot gas is not enough, they add more fuel. So there's supplementary firing here. But the point is, this would be as if that steam cycle is running for, the steam cycle, it's as if it's running for free. It's like basically you're running on the waste energy from the exhaust of the gas turbine. So when you put a gas turbine power plant on top of a Rankine cycle, this is called combined cycle. Okay, and this Rankine cycle by itself, no matter how many feed water heater you add, I mean here, this was, as you know, this was the final last year. I gave them this and I told them to write the code for it. That is a solution. So this is a simulation for this cycle. So with even 7 feed water heater and a reheater and a superheater and all those things, what is the efficiency going to be? What do you think the efficiency of a steam power plant would be? And let's go super critical and everything. We are talking 40, right? We are talking about 40, pushing 40, right? We're going to be 40. But you put a gas turbine on top, and we are talking 65. So we go from 40 to 65. Why? Because again, the steam plant is, when you calculate the efficiency for this, so at the end he says, calculate the combined cycle efficiency and the gas turbine cycle efficiency. So the combined efficiency would be what? Work net here plus work net here divided by this Q added, right? And if there is Q added here, you also add it. That would be the combined cycle. And the work cycle, the efficiency of the gas turbine by itself would be this work over this Q. So gas turbine by itself is like 30 efficiency, more or less 30 stuff. Steam by itself is like 40. You put the two of them together and you go 65. And so that concept, as I told you or not, maybe I didn't, this concept was the first time it was invented in the whole world was in Bartsville, Oklahoma. They had some steam that was left over, and they said, let's use it to actually have some power out of it. And so the concept of heat recovery boiler was created. Okay, and now basically this is the way to, if any new power plant that's burning gas actually run on this. Because why would you have 40% if you can get 65%? Right? So, so how are we gonna do this? So here, in this project, he basically said you are required to calculate the surface area of the 3 parts of the heat recovery boiler: the superheater, the boiler, the economizer. Okay, and he's giving us information about this cycle. He's giving us the pressure ratio 8 and the temperature here 5,000 Kelvin. Sorry, 2,000 Rankine. No, he gave us T3. So T3 2,600 Rankine and T5 after the supplementary firing. It become 2,000. Okay, and then he said the steam leave, the hot gases leave here at 800. So you need to know how to simulate or like how to calculate a gas turbine. He said this gas turbine, for simplicity, assume the gas turbine run on an ideal Brayton cycle. Who had Brayton cycle in Thermo 1? Raise your hand. You have heard about Brayton cycle before. One person. One person heard about Brayton cycle. Everyone else did. So let's revise the Brayton cycle. So the Brayton cycle is the cycle for any jet engine, any gas turbine. Okay, so how it will look like on a TS diagram. It look like this. Those are two constant pressure lines. B constant, E is constant. 1 and 2. Ideally, you go isentropic up. In real life, no, you go a little bit to right or left. Right or left, ideally, like real life. Right, it needs to be here somehow, right? And then you add fuel, and then you hit the max, which he said, this is 2,600 Kelvin, no Rankine. And the Rankine is like 0.5555555555556 Kelvin. Okay. So this is 3, and this is 4. And the pressure ratio, he said B2 over B1 is 8. And that's also happened to be B3 over B4. So the compressor run on the same pressure ratio like the turbine. And so 4 is not hot enough to go to the steam power plant. So he will heat it in supplementary firing a little bit to go to 5. And so 5 is heated all the way to 2000. And then, so you add fuel in 2 parts then. You add fuel here, and you add fuel here. And then you expand, or like you basically use this so that you can generate steam all the way down to 6. And you say T6 is 800. Right? So this Rankine cycle, this Brayton cycle, which consists of a compressor, 1, a combustion chamber, 2 to 3, and a turbine. Sitting at the same shaft, and then this is connected to a generator. They take you to 3 to 4. This is the compressor, and this is the turbine. So, like always, work compressor, Q added, work turbine, everything is M dot delta H. Okay, but it gets easier now because the work compressor, which I'm gonna say M dot say air H2 minus H1, that H, we can easily say it's CP T2 minus T1. So the H becomes CBT, okay? And for simplicity, they just, in this project, they said use CP always constant. The CP is always 105. So the CP is 1005 joule per kilogram Kelvin. So that's pretty easy, huh? Work turbine is M dot air CP T3 minus T4. Q added, right? Q added for the Brayton cycle or the gas turbine is M dot A CP time what? Help. Someone help me. This is where we put the fuel. So Q added is how much? 3 minus 2, right? And the efficiency, eta thermal for the cycle will be work net over Q added. Okay, and work net would be work turbine minus work compressor divided by Q dot. Make sense? Okay, now the only problem is I got I don't have T1, but I can assume T1, right? So we can assume T1 equal to say 25 degrees C. Okay. But I don't know T2. I need T2. T3 was given, but T4 was not given. So my problem is I need T3 and T2 and T4. So how can we get that? If you know T1 equal 25 degrees C, how do you calculate T2? And by the way, you know that B2 over B1 is 8. And that's the same problem here too. If you know that T3 is 2,600 Rankine, and you are asking about T4, it's the same problem. So can someone help? Say that again.
T2 would be 200.
Why?
P1 by 8.
No, that's the pressure ratio, not the temperature ratio. So who said that the pressure and the temperature would be the same ratio? They are not, but they have a relation. What's the relation between the pressure ratio and the temperature ratio? For what? For isentropic compression. If you go up isentropically for ideal gas, don't use this for steam. For ideal gas, if you go isentropically, there is a relation between the temperature ratio and the pressure ratio. What is it? T2 over T1 is B2 over B1. Yes, the pressure will increase, the temperature will increase, but how much? Over K, right? And I personally always get confused. Is it K minus 1 over K or K over K minus 1? What is that K? What is that? K is the specific heat ratio. For air, it's 1.4. That is basically Cp over Cv, right? And actually, the only thing that remind me or like tell me that this correction is correct or wrong is that I remember it's CBT and RP in the entropy calculation. And so the Cp is actually gamma R over gamma minus 1. And so that's why the R cancel with the R and then the P raised to gamma minus 1 over 1. Okay, but you check. I mean, you don't have to memorize again because the exam is open book. So you can check. But the point is now, if you know the relation between the pressure and temperature, then knowing T1 and the pressure ratio, you got your T2. Knowing the temperature and the pressure ratio, you got yourself T4. Okay? Yes, B1 is atmosphere. That's correct. 1 bar. Let's call it 1 bar. Correct. We have B2. But how does that tell us about T2? No. This is not on a steam cycle. This sketch that I'm plotting Brayton cycle, you don't plot this on the TS diagram of the steam and read from it. T and S. But having said that, yes, it's T and S. Let's make it bigger. It's T and S, correct? But I cannot plot those temperature and pressure, which this is what, 25 degrees C, and this is 1 bar, and this is 8 bar. You cannot go to the steam table and put this point there and say, here's point 1. You need what? You need the TS diagram of air. Exactly, right. So this is weird because in the project, I tell you, I want you to plot the two of them. So listen carefully because this part is really confusing. I thought that it was horrible for me to write this, but please look at this. Please plot the two cycle on the TS diagram for water vapor. So I hope that is clear. For water vapor. So what I'm asking you to do is, on the TS diagram of the water vapor, which will look like this, and we will have, you know, whether we're gonna have a heat or not, maybe we shouldn't have it, just like this, right? And it's gonna be like this, and then there is like, I think that he had what? He had 2 feed water heater. Was it 2 feed water heater or 1? I think 2, there was 2. One was open and one was closed. Anyway, you make your stuff, right? And it's basically, you know, whatever. And so here is, this guy is ready to go to the turbine. And let's say this is the part where it go to the feed water heat, the boiler. So this is our economizer. And this is our boiler, and this is our super heater. So all I'm asking you to do is, on this diagram for water vapor, I want you to basically come and say, then the Brayton cycle will be like this. Here is when you go in with 5, and here is where you would leave at 8, right? Or whatever. Actually, this was 0.6. We call it 6. And this temperature here was 800 Rankine. And this temperature here at 5 was how much? How much? No, 3,000? No, 2,000. It was 2,000. He heated it all the way to 2,000. So, and then you continue the Rankine cycle here, because like 4 was like this. Then let's delete this. And 4 is like this, and so here is 1, 2, 3, 4, and then you take it to 5, and then you cool it back to 6. So this is confusing because all that blue is really sitting on top of the black on not the right page. You understand? Like we're imposing the blue as just a cartoon. I mean, you can, not a cartoon, I mean, you can use the temperature scale on the TS diagram, but just realize that we will use, I think you should use, of course, the scale of the T, right? So, I mean, this should really set in the right temperature, and this should read in the right temperature and right temperature and right temperature. But you just need to realize that don't read the H, for example. Don't read the H or the entropy or anything. Got it? You're just plotting the Brayton cycle on top of the Rankine cycle so like let's make a cleaner sketch. So the the Brayton cycle is doing this. So here is 4, 5, 6, 1, 2, and 3, right? And during this, there is basically this part. Superheat, boiler, economizer. That is a sketch that you guys need to plot. You see how the superheat, the boiler, and economizer. And so what's really required from us is, and so this is the TS diagram of the water vapor. So we need the area. We need the area here, the area here, the area here. So what that tell us? I'm going to use the heat transfer equation. I'm going to use Q equal MUA delta T, right? So I need my delta T. I need this temperature, this temperature, this temperature, and this temperature. What is that temperature? And over here, I need this temperature. So in each section, I mean, let's take the superheater as an example. I know that this is the superheater. So the air is being cooled from 2000 Rankine to a temperature here that I don't know. And the water is coming at, he actually told us the pressure. He told us the pressure and the temperature. How much is it? He said the water is, the steam is generated at 12. So this is 1200 PSI absolute, 1200 PSI absolute. And the temperature is 1560 Rankine. Okay, so of course you'll be able to calculate this temperature. This, for the superheater, this would be called TC in, and this is TC out, right? And for the air, this is TH1 and this is TH2. So to calculate the area, I need the 4 temperature. Then I can use Q dot is UA logarithmic mean temperature difference. So do I know the Q dot? Help. Help. It's Q dot cold, right? M dot steam, right? H, right? H, I guess we just call those points something in the cycle. I don't know what you want to call them, 13 and 14, something. So it's H14 minus H13. So now your question is, well, how much is my M dot steam? So I can calculate this Q dot, then I'll be able to calculate the, so if you manage to do this, then it's also happened to be M dot air, and it will be the 2000 minus the temperature that we want to find out how cold it will get times CP. M dot air times CP. That will be Q dot hot. So this equal to this. So this is the essence of what you're going to do in every section. You will do a thermal balance between the energy of the hot and the cold, and that will allow you to get all the temperature, 4 temperature. And then from those 4 temperature, you'll be able to calculate the area. Okay? And in the project, he said that like he just wants you to run the calculation at task 3, very simple calculation. So he said in part 3, calculate the heat transfer rate for the 3, their inlet and exit temperature and surface area using counterflow arrangement. So just for simplicity, he said just assume counterflow. So the F is 1. The F is 1, and you just say Q is UA delta T. Get the delta T, you'll be able to calculate the area. But then in task 4, in the detailed design, when you want to go a little bit more, then you would say now use more accurate geometry. Is it really counterflow? You need to check in heat recovery boiler. Is the radiator, sorry, is the superheater set in really counterflow configuration or not? So in that in the book of the MIT, or actually even in the heat transfer book that you guys had, there is, where is it? There is a configuration of, did you show you the picture of the superheater? And it is not. It's not counterflow. It's, I would say, Ouch. I would say it more looked like a shell and tube, really. That was a big shell. Yeah, see, it looks something like this, where the hot gases will go through them. So anyway, or like this is even a better picture. I had a friend that worked for BSO and he showed me, actually, I think I have those pictures, I'll send it to you. He showed me a superheater after so many years of operation. The pipes kind of like get, rather than straight, they kind of lag, you know, because of the heating. You know, thermal creep over a long time. So so then you will continue this part from the boiler. The hot gases continue doing this to another temperature, while the steam is now going from HF to HG, right? And same story again. You know exactly the temperature of the steam. You know the m dot. You'll be able to calculate this. You'll be able to calculate the temperature. And you have the 4 temperature, you'll be able to calculate that. And finally, this part. Okay. So to help with this, I also give you the code to simulate this cycle. I mean, you don't have to stick to this with one closed feed water heater and one open feed water heater. You can basically just do this one. And so all you have to do is just like cut and paste this into your MATLAB and it could run. But the only problem with this guy is that he has a reheater and we are designing a heat recovery boiler with only superheater and boiler and mine. So I'm saying I don't care about this, can do anything here, but I care about this, that you need to have only the 3 parts. So if you're going to use that code, maybe you need to go and delete cut the reheat part. Find the reheat part and remove it, basically. Right? And when it comes to the, you see the Q added, he's doing the superheater, the first part plus the reheat. So you may want to modify this part. But it's super nice that you have the whole code simulate this. So finally, it seemed that we need m dot steam and we need m dot air. So actually what we really need is not both of them, we just need the ratio between the 2 of them so that we can calculate the cycle efficiency. So how do we calculate the ratio between m dot steam and m dot air? This m dot air going through this and m dot steam going through this, are they twice as much or 3 times as much? How do we do that? How we calculate this, guys? Say it. How can I get the ratio between m dot steam and m dot air? Where is the place where they come in contact with each other? Where? Where does the steam and the air come with contact with each other? The heat recovery boiler. The gas, the air go from 5 to 6, while the steam going from liquid to superheated. So how do I get the ratio between m dot and m dot? Q, right? Say Q equal Q. The Q that this guy loses is equal to the Q that this guy would be. So what we have been doing in every section, if we actually do it over the whole 3 sections and just tell yourself 5 becomes 6. 5 becomes 6 so that your steam that's coming here become there. Let me call this point A and this is point B. So that's easy. M dot air, CB air, T5 minus T6 equal to M dot steam time what? Help me. Huh? A minus M, what? Yeah, HP minus HE, correct. HB minus HE. So HB, we know the pressure, we know the temperature. We got it. Point A, we know the pressure and the temperature. Temperature of point A, the temperature of the point that will actually go to the boiler will depend on what will decide the temperature of the water going to the boiler. What? Huh? What will determine this temperature? So we said in order to find out the ratio between m dot air and m dot steam, we need to do energy balance on this. And to do energy balance on this, we need to know the H going into the turbine. That's stated by the problem. The customer said, I want that pressure temperature. But the question is, what is the temperature leaving here? Of course, it's the same pressure. We always assume boiler is constant pressure, right? But what is the temperature leaving here? It will depend on how many reheating how many economizer and feed water heater you're doing. Are you going with this design, or you are going with this design, right? So you will pick the part here to tell I'm gonna have that temperature. And so once you know the temperature coming in, then this temperature minus this temperature, will tell you the energy that this guy required, which will tell you how much m dot air is coming here, and then you can size that heat exchanger. You can size the whole cycle now. Okay, make sense? Yes. Okay, good. So your quiz right now. So now your quiz today's quiz is super easy because we had a hard time in the exam. So out of my nice personality, you have an easy quiz today. So if you open the assignment, you will see under quiz 7. 80%, just to say, are you online? Or if you are in class, you write the seat number in front of you. And 20% on a TS diagram, please plot an ideal Rankine cycle with reheat stage and one open feed water heater. I think it's really important, and I saw weird drawing in the exam. So let's just plot an ideal Rankine cycle with a reheat and one feed water heater. A sketch, basically. And that's it for today. You finished that quiz, and you guys are done. Thank you so much. So the question is, are we allowed to just make one if we cannot print out the TS diagram? Yes, you don't have to print an actual TS diagram, but you just have to make it neat. Make the pressure line, under the dome constant, make it neat. Don't have to print an actual TS diagram. This is just a sketch. But I guess Pippin will take points if you don't do the open part right. Remember how the open part goes to saturated? And he has to have a pump before and pump after. All open feed water heater need to have a pump before and pump after. Unlike the closed feed water heater that they can just run all with one pump.